So we have here for the introduction of steel, principles of steel structures. Again, for the whole duration of our subject, we will be talking about steel. But not all steel are considered structural steel. We will be considering here yung tinatawag nating structural steel. Meaning, pagka sinabi nating structural steel, ito yung type ng steel na merong adequate na stiffness and strength which are capable of resisting yung tinatawag nating structural loads. Okay? So, kailangan it could be a structural element or structural member. It could be in the form of beam, in the form of column, or in the form of trusses. So, yun yung pag-uusapan natin na steel dito sa subject natin. Yung tinatawag nating structural steel. Okay. So, pagka sinabi nating steel, from material science, it is an alloy of iron. Pagka sinabi nating alloy, it consists actually of two or more elements. Basically, yung steel, it is composed of iron and yung carbon. Pagka steel. Okay? So, iron is actually the principal component. This is the majority component of the steel. Tapos, small percentage lang yung sa carbon. Actually, in manufacturing of steel, minomonitor yung amount of carbon. Linilimit yung amount of carbon in manufacturing steel. Why? Yung carbon kasi nagko-contribute yan siya sa strength ng bakal. Yes, nagko-contribute siya sa strength, but at the same time, rini-reduce na yung tinatawag nating ductility ng bakal. Okay? So, I think I gave you a research work about the properties of steel. At isa sa properties ng steel is yung tinatawag nating ductility. Okay? So, ano yung ductility? Ano yung ductility property? Ito yung tinatawag nating makunat. Okay? So, di ba pag ang steel, pag hinila mo siya, nag-stretch siya, nag-elongate without even breaking easily. So, hindi siya nagbe-break agad-agad. Hindi basta-basta napuputol. Kumbaga, kaya nang mag-resist ng deformation ng hindi basta-basta napuputol. Okay? Yun yung tinatawag nating property ng steel na ductility. This is contrary actually sa concrete, sa RC, kasi pag hinila mo, tinitension mo yung concrete, nagkrak-crack kaagad siya. Bumibitak. Okay? So, magandang property ng steel, isa sa magandang property ng steel is yung tinatawag nating ductility. Okay? Para ma-sustain yung ductility ng steel, linilimit yung tinatawag nating carbon. Okay? So, yung this is only limited yung tinatawag nating carbon. We also have here the ASTM or yung tinatawag nating American Society of Testing and Materials, ASTM designation. So actually, the American Society of Testing Materials, ito yung group sa Amerika na nagmo-monitor ng lahat ng structural materials. And they are also the ones who give designations or yung mga pangalan ng bakal, ng ASTM. So according to ASTM, for ferrous metals, the designation has the prefix letter A, yung aurum, followed by 2 or 3 numerical digit. Okay, so we have here yung example natin, astm A36. So ito yung pinaka-common na bakal dito sa Pilipinas. Yung ASTM, yan, naka-fix yan sa pangalan niya. Ibig sabihin yan, nag-comply siya doon sa requirement that is set by the uh, American, yung ASTM, the American Society of Testing and Materials. So, nag-comply siya doon sa requirement or pinasan niya lahat ng laboratory test set by the ASTM standards. So, kaya may ASTM A36. Pagka mapapansin nyo, yung mga 2-digit, for example here, pagka sinabing ASTM A36, yung 36 dito, actually is the FY, yung yield natin. So, pagka sinabing A36, alam mo na yung FY niya is 36 KSI. So, pag kinonvert mo yan, sa SI, 1 KSI is equal to 6.9 MPa. So, approximately yan, 248 MPa. Kaya yung A36 natin, yung magkakaroon tayo ng approximately 248 MPa or 36 KSI. Yung A514, hindi porket 514 yan, ibig sabihin 514 KSI na din yung ating yield strength. Hindi it's just a numerical digit or designation set by the ASTM. So pagka sinabi nating A50, alam natin, that is 50 KSI. Okay? Yung yield strength niya, yung FY natin. Okay? So now, may dalawa tayong paraan ng manufacturing ng steel. Okay? Meron tayong dalawa. Yung tinatawag nating hot rolled, ito yung pagtutuunan natin ng pansin dito sa subject natin. At yung pangalawa, yung tinatawag nating cold form. Okay? Yung hot rolling, tapos yung cold form. Yung mga hot rolled, yun yung mga products, ito yung mga ginagamit sa structural ng mga buildings. Okay? Yung cold form, ito yung mga light gauges, yung mga maninipis, ito yung mga ginagamit sa maliliit na structures like residential. Okay? So, sa hot rolled, ito yung mga solid na bakal. Yung cold form, ito yung mga light gauges, yung medyo maninipis. Maninipis lang siya relative compared doon sa hot rolled. Mamaya, magpapakita ako ng picture na difference ng hot rolled and yung sa cold form. Okay? So, dito sa subject natin, doon tayo sa hot rolled. Okay? Sa hot rolled, dito sa buong subject natin, hot rolled yung pag-uusapan natin. Okay? So for hot rolled, we have here the 3 types of hot rolled structural steel used in building. So una, yung carbon steel. Pag sinabi natin carbon steel, yung FY niya is in between 220 hanggang 290. Okay? So actually, yung A36 is 250, 248 or approximately 248 MPa. Pasok siya dito. So carbon steel yung A36 natin. Okay? Meron din tayong high strength, low alloy steel. So we have the yield strength 480 to 840. Ito yung medyo mas matitibay na bakal compared doon sa carbon steel. Okay? Meron din tinatawag na quench and tempered alloy steel. Okay? So we have here yield strength 480 to 690. Okay? So, ito yung mga bakal na nag-undergo ng quenching or yung tinatawag nating tempering. So, yung quenching or yung tempering, these are steel treatments. Okay? Steel treatment ito. Ibig sabihin, ito yung mga processes or yung mga proseso kung saan ginagawa ito sa bakal to better improve the property like increasing yung tinatawag nating yield strength, yung FY, or yung other properties ng bakal. So, ginagawa itong steel treatment to improve the property of our steel. Okay? So, we have here, yung example na treatment na ginagamit sa steel is yung una, yung tinatawag nating quenching. Okay? So, pagka sinabi nating quenching, ito yung bakal, nilalagay siya sa higher temperature or yung mataas yung temperatura, more than 1,000 degrees centigrade. Tapos, after reaching a certain temperature, sinasubmerge siya sa quenching liquid. Okay? Siyempre, yung quenching liquid na yon have a relatively lower temperature, kaya nagkakaroon siya ng biglaang pabagsak ng temperatura. Okay? So, yun yung tinatawag nating rapid cooling. Okay? So, yung process na yun yung tinatawag ng quenching. Okay? And they believe na yung quenching is the process to improve the property of steel. Okay? Meron din tayong pangalawa, which is the tempering or yung tinatawag nating reheating. Okay? So, they believe that reheating improves the properties of our steel structure. Okay? So, we have here the hot rolled. Ito yung example ng hot rolled. Ito din yung cold form steel. Okay? So, yung hot rolled, meron tayo dito the wide flange, the S section. Actually, wide flange and X section is an I-beam. I-beam ito. Meron din tayong channel. We have an angle. And we have a T section. Okay? So, yung pagkakaiba ng wide flange saka yung S section, yung W section, yung lapad niya, yun din yung tangkad niya. Yung lapad dito, yun din yung tangkad niya. Compare doon sa S, medyo matangkad na letter I yung sa S. Okay? And we have here an example of chord form steel. Ito yung mga light gauges lang. Okay? So, ginagamit siya sa wall panel, steel framing, yung cut and pre-cut stud, ginagamit yung mga cold form steel. Okay. So, for the duration of our subject, mag-focus tayo doon sa may hot rolled steel. Okay? We also have here the stress-strain diagram. I think merong discussion doon sa module ninyo. I hope that you have read that part. Okay? Actually, sa strength of materials ninyo, na-discuss na ninyo ito, yung stress-strain relationship. Uulitin ko lang ito, pahapyawan lang natin ito. Okay? So, this is actually yung pinaka-life cycle ng bakal. Okay? So, for the y-axis, ito, meron tayong stress, yung force over area. Okay? So, for example, we have here steel, meron tayong bakal dito. Ito, tapos pag nag-apply ka ng tension, hinihila mo yan, nagkakaroon yan ng strain. Okay? Since nagkakaroon yan ng elongation. Pag hinila mo yan, pag nag-apply ka ng force, magkakaroon yan ng elongation. So, let's say yung elongation mo, let's say, i-designate natin delta. Okay? So, yung delta na yan, dinidivide natin siya sa original length nung ating bakal para makuha natin yung strain. Okay? So, kaya yung strain natin nasa x-axis. Ito yung strain natin nasa x-axis. So, yung y-axis natin stress and yung x-axis natin is strain. Okay. So, at that instance na tinetest mo yung bakal sa UTM, makakakuha ka ng certain points, di ba? Yung force at saka yung strain points. So, pag hinihila mo yung bakal, nagkakaroon ka ng points due to the force and yung sa may strain. So, pagka-clean up mo yun, yung mga certain points na yun, ito yung magiging itsura ng graph. So, ito, yung stress-strain diagram. So, i-assess natin kung anong mangyayari doon sa bakal natin in the process na tinetest natin siya. Okay? This graph is actually a typical diagram of a ductile mild steel. Okay? Yung low carbon steel. So, magsa-start tayo sa zero. So, start tayo sa zero. Siyempre, zero kasi wala pang nangyayari. Hindi pa tayo nag-start ng test. Okay? So, after which, pagka nag-apply ka ng load, pagka nag-apply ka ng force doon sa UTM, di ba? Pag sa UTM kasi hinihila yung bakal mo. So, pagka nag-apply ka ng force, hinihila, nagsa-start ng hilain yung bakal mo, mag-uumpisa ni din siyang humaba, nag-elongate. Siyempre, pag ito yung bakal mo, pag nag-apply ka ng force, magsa-start yan, mag-elongate, or maghahaba yan. Okay? So, yung una, sa umpisa, kung ano yung in-apply mong force, sa umpisa, to, pansinin nyo itong straight line, sa umpisa, kung ano yung in-apply mong force doon, ganun din yung paghaba niya. So, ibig sabihin, proportional siya. Hanggang sa tinatawag nating proportional limit. So, andito yung proportional limit natin. Okay? So, pagka mapapansin mo, yung graph from 0 to the proportional limit, straight yan. Straight line. Ibig sabihin yan, stress is directly proportional doon sa ating strain. Okay? Kasi kung ano yung force na in-apply mo, yun din yung paghaba ng yung section or yung material mo na steel. Okay? Kaya yung graph natin is straight line. So, meaning, constant yung slope natin. Okay? So, anong tawag natin dyan? Di ba yan yung tinatawag nating Hooke's law? Stress is directly proportional to strain. That's Hooke's law. Okay? So, hanggang dito sa may proportional limit. So, hanggang dito, sa proportional limit, hanggang dito. Pagka hinila mo kasi yung steel mo or yung bakal mo, tapos binitawan mo, babalik siya sa original shape. Okay? Beyond this proportional limit kasi, pagka hinila mo yung bakal mo, beyond this proportional, pagka na-reach na yung elastic, yung tinatawag nating elastic limit, and they go beyond it, tapos binitawan mo yung material mo, hindi na siya babalik sa original shape. Ibig sabihin, nag-deform na yung shape ng ating material. Okay? So, hanggang dito sa proportional limit, pagka ini-stretch mo, tapos binitawan mo, babalik at babalik siya sa original shape niya. So, beyond that, hindi na siya babalik sa original shape, magde-deform na yung ating material. Okay? Until such time na ma-reach natin yung pinatawag nating yield point. So, ito yung yield point natin dito. Ito yan. Ito yung tinatawag nating yield point. Kung mapapansin ninyo, yung graph doon sa yield point, medyo bumaba siya. Tas naging horizontal. Ibig sabihin na nagbabago yung stress. Hindi nagbabago yung stress. Pansinin nyo ito. So, pagbaba, tapos medyo naging horizontal siya, nagganon siya. Okay? Ibig sabihin nito, hindi na nagbabago yung stress natin kasi ito yung nasa y-axis yung stress. Pero yung strain natin nag-i-increase pa rin siya. Strain is in our horizontal. So, sa bakal, nangyayari yon, yung tipong ini-stress mo siya, time will come na kahit hindi mo na nagdagan yung force or yung pwersa na in-apply mo doon sa bakal, continuous pa rin nag-elongate yung bakal. Okay? Yun yung tinatawag nating, pag sinabi nating nag-yield na yung bakal. Yun yung tawag natin yun. Yung kahit hindi mo nadagdagan yung pwersa, nagpo-continuous nag-elongate pa rin yung bakal natin. Tawag natin doon is yielding of steel, or nag-yield na yung bakal natin. Okay? So, since sa steel, yung test na ito, marireach ng steel yung tinatawag nating yield. After yield point, nag-yield na siya. Tapos, 'di ba, after 12 times after nung yield point, ang susunod na diyan ay yung tinatawag nating strain hardening. So, yung strain hardening hanggang dito sa yield, papunta dito sa ating may tinatawag nating ultimate strength. So, yung process dyan is yung strain hardening. Okay? So, yung seasonal sa yielding, pagkatapos mag-yield ng bakal, after 12 times after that yield point, yung magsa-start na mangyayari sa bakal is nag-strain hardening na siya. Until such time na ma-reach niya yung peak point natin. Ito na yung tinatawag nating ultimate tensile strength niya. Okay? So, pagka pinoject mo ito, yung ultimate strength, yung pinaka-peak point, pagka pinoject mo doon sa ating y-axis, ito na yung tinatawag nating FU. Diba? Pagka pinoject natin yan. So, pagka maalala yun nyo, pag 836 ang steel ninyo, ang FU natin is 400 MPa. Okay? Yung Fy naman, yung sa may yield point, pagka pinoject nyo yan sa y-axis, yan yung magiging Fy. Okay? So, kung mapapansin ninyo, FU point, yung FU natin, yung point of FU natin, mas mataas kaysa doon sa ating Fy. Okay? Mapapansin nyo, mas mataas yung FU, which is 400 MPa, tapos yung Fy natin 248, for example, for an 836 steel. This only shows that is the steel exhibit yung tinatawag is truly a ductile that exhibit yung tinatawag nating yielding. Okay? So, nag-yield muna siya bago siya mag-ultimate, yung ductility ng ating steel. So, pagka naka-encounter kayo ng material na mas mataas yung ating Fy kaysa doon sa Fu, baliktad. Pagka mas mataas yung Fy kaysa doon sa Fu, ibig sabihin, hindi nag-yield yung material. Okay? Hindi siya nag-yield. Ulitin ko, ano ba yung yielding? Ito yung kahit hindi mo nadagdagan yung pwersa, nag-elongate pa rin yung material natin. Yun yung nag-yielding. Di ba? Okay? Pero pagkabakal yung pinag-uusapan natin, parating mas mataas yung Fu niya kaysa doon sa Fy. Kasi ang bakal nag-yield yan. Kasi ang bakal, may property siya na yung tinatawag nating ductility. Okay? Nag-yield palagi yung bakal. Okay? So after noon, after niya ma-reach yung tinatawag nating ultimate strength, magkakaroon na tayo ng rupture. Okay? So meron tayong dalawa. Ito. Meron tayong pababa, tapos meron tayong linya na pataas. Pag mapapansin nyo. Okay? So, yung fracture point dito sa taas, ito yung tinatawag nating theoretical rupture. Tapos, yung itong line na ito, yung biglang pagtaas niya, yan yung tinatawag nating actual rupture. Okay? Yung theoretical rupture, itong yung nasa baba, yung theoretical rupture, ang pag-compute sa stress dito is based from the original diameter ng rebar. Kaya mas mababa siya kaysa doon sa actual. Kung ano yung original diameter ng rebar, yun din yung gagamitin mo sa pag-compute ng stress dito sa fracture point dito sa baba. Okay? Kumpara doon sa actual, dito sa actual, mas mataas siya. Bakit? Since yung stress dito sa actual is calculated based on the actual diameter at failure. So, ano yung actual diameter ng failure natin? Siyempre, mas maliit yung diameter niya at failure since nagkakaroon tayo yung tinatawag nating necking. Okay? So, tignan ninyo dito sa drawing dito sa kaliwa. Ito yung tinatawag nating necking. So, pagka hinila mo yung bakal, lumiliit yung diameter kung saan mapuputol yung bakal natin. Yun yung tinatawag nating necking, yung pagliit ng diameter. So, yung diameter dito, ito, sa may necking. Ito yung gagamitin natin to compute for the stress dito sa ating actual rupture. Kaya mas mataas siya. Siyempre, mas maliit yung diameter na gagamitin natin. Okay? Unlike doon sa theoretical na yung gagamitin natin na diameter is yung original diameter nung rebar. Okay? So, ito yung pinaka-life cycle ng bakal. Since I want you to understand kung paano nag-work yung bakal from start until doon sa failure during testing. Okay? So, I want you to understand na maraming pagdadaanan ni stages yung bakal. Like, for example, dadaan muna siya sa proportional limit, tapos mag-elastic limit, tapos sa yield point, tapos strain hardening, tsaka pa lang siya mag-rupture or mag-fail. Okay? So, bakit kailangan natin malaman itong stages or yung tinatawag nating life cycle ng steel o yung bakal natin? Okay? Remember, meron tayong dalawang design process or yung design concept sa steel. Okay? So, gagamit tayo ng yung tinatawag nating AST and yung LRFD. Ito yung dalawang process na gagamitin natin sa design concept sa steel. Okay? So, we will both discuss this in the future, yung ASD and LRFD. Okay? So, pero pagka sa activity ninyo or quiz or exam, pagka hindi ko binanggit kung anong gagamitin, ASD ba or LRFD, palagi niyong gamitin yung LRFD. Okay? LRFD tayo. Okay? So, pagka sa ASD kasi, ang konsepto ng design dyan is based sa behavior ng bakal within dito sa ating elastic limit. Okay? Within dito sa elastic limit. Yan yung i-consider natin pag ASD yung design concept na gagamitin natin. Okay? So, ibig sabihin, ang assumption natin is yung strength ng bakal is hanggang sa range lang na yan. Gagamitin natin sa ASD. So, tapos yung LRFD naman. Sa LRFD naman, ang assumption natin is sa may plastic. Okay? Sa LRFD, ang assumption ng LRFD in such a way that the strength is within dito sa plastic range. Diyan. Papunta dyan. Yung plastic range. Plastic limit. So, pagka sinabi nating plastic limit, ito yung behavior ng bakal beyond yielding after siya mag-yield. Okay? After siya mag-yield, plastic na siya. Before siya mag-yield, elastic pa lang siya. Okay? So, get? So, again, bago mag-yield yung bakal natin, elastic pa lang yung ating bakal. So, ang gagamitin natin dyan, ASD. Okay? And after mag-yield, magiging plastic na yung ating bakal. So, LRFD yung gagamitin natin. Okay? So, after yielding, LRFD na yung gagamitin nating method. Before yielding, ASD yung gagamitin natin. Okay? So, yun yung dalawang concept ng design ng steel. Gagamitin natin yan later on. Okay? So, pagka ASD, ang gagamitin natin dito is yung tinatawag nating working loads or yung unfactored loads. At sa LRFD naman, ang gagamitin natin is yung factored loads. So, yun yung main difference ng dalawa. Okay? We also have here the typical structural steel. Okay? So, ito yung designation natin. Okay, so we also have here the structural steel shape. Meron tayong wide flange, channel, and angle bar. Okay? So, meron ito sa module ninyo. Kung ano yung thickness, TW, thickness ng web, BF, yung base ng flange, for the channel, and for the angle bar. Okay? So, punta tayo dito sa designation. meron akong W920 by 270.80. Yung 920 na yan, ito is the approximate depth. Pagka SI in mm. Yung unang value, yan is yung approximate depth natin. At yung pangalawang value, ito yung weight nung beam. Okay? Weight ito ng beam. So, pagka SI, ang weight natin is in kilogram per meter. Pagka English yan, ang approximate depth natin is in inches. Tapos, yung weight natin is in pounds per feet. Okay? So, yan. Pagka sinabi natin W30 by, say, 21. Okay? So, yung 30, ito yung depth natin. 21, ito yung weight ng beam natin. Pagka English ito in inches, ito in pound per feet. Okay? So, yan yung designation ng bakal. So, pagka tinignan ninyo later on yung ibibigay kong Excel, magbibigay ako ng Excel na tawag nito, properties ng steel, yung BFT, thickness ng web for the standard section for us to have uniform values para magkaroon tayo ng uniform values. You can use actually other book or other references, steel manuals, pagka standard section. Kasi meron ng binigay yung AISC na properties ng steel. Meron ng BFT, WTF. Meron yan. However, yung gagamitin natin throughout the duration of our subject is yung ibibigay kong naka-Excel for us to have a uniform values. Yun yung gagamitin natin. Okay? Para magkaroon lang tayo ng uniform values. So, pagka hindi ko binigay sa activity ninyo, pagka sinabi ko lang W12 by 21, tignan ninyo yung properties niya doon sa ating Excel na ibibigay ko later on. Yung BF, TF, TW, lahat given yan sa standard section. Okay? So, doon kayo titingin para magkaroon tayo ng consistent na values. Pare-parehas tayo lahat. Okay? Kasi sa ibang reference kasi kayo, merong konting discrepancy na sa values. For example, pagka yung BF ko is 233.30, yung ibang steel manual 233.32, mga ganun. May konting discrepancy lang sa ibang manual. Okay? So, gagamitin natin is yung ibibigay kong Excel. Okay? So, pagka tinignan ninyo din doon sa steel manual, pagka sinabi kong W12 by 21, pagka tignan ninyo yung depth niya, hindi siya 12 inches na sakto. 12.1 inches, mga ganun. Okay? So, yung nasa designation, ito is actually the nominal values. Ito yung actual values ng properties ng steel. Kaya pagka kinompare ninyo, may konting discretion point something, may discrepancy. So, ito yung actual na depth nung W section. Okay? So, yung nasa designation, yan lang yung nominal values, tapos ito, yan yung actual. So, anong gagamitin natin? Ito, yung nasa actual. Kasi since meron naman kayong Excel. Okay? Yung mga actual values yung gagamitin natin later on sa mga activities ninyo. Okay? So, we also have here the section properties. The dimension, area, or perimeter, center of gravity, moment of inertia, section, modulus, and radius of gyration. Actually, you have discussed this on your lower design. Okay? So, medyo i-review lang natin since gagamitin natin itong properties ng steel in the design and analysis of steel section. Okay? So, we have the centroid of area, yung transfer formula. Ito yung transfer formula natin. Gagamitin natin yan to transfer yung ating centroid, especially if we have a build-up section. O moment of inertia. And radius of gyration. Polar moment of inertia. At ang mga importante ito na properties ng steel, since gagamitin natin yan in the analysis later on for the steel section. So I hope that you have read the given properties ng steel doon sa module ninyo. I also have attached yung mga formulas. So kindly memorize them. Yung radius of gyration, that is the square root of Ix over A. So, memorize din nyo yan by heart. Since palagi nyong gagamitin yan yung mga properties ng steel. So dapat alam nyo ito. Memorize the formulas by heart. Okay? Hindi dapat nakakalimutan ito kasi this is the basic formulas ng design and the analysis. Palagi nyo itong gagamitin. Okay? Okay, so let's have an example for the determination of the section properties of build-up section. So the problem says that we have to calculate the combined section properties of the build-up section shown. So it is composed of a wide flange section W21 by 83. So ito yung wide flange natin. And we have a C section, channel section, C15 by 50 on top of it. So ito yung ating channel section. So for the W section, ito yung given natin. So ito yung wide flange. As you can see, the wide flange section is on its upright position. Okay? So, pag tinitingnan natin ito yung wide flange natin. The flange section is on its upright position. And it's on its upright position, the following properties are given. So, ito yung properties ng wide flange in this position. So, naka-upright siya. Okay? While for the channel section, on its upright position, ito yung position ng channel section natin. Ito yung properties natin for the channel section. Ito yung mga properties niya in this position. Naka-upright yung C channel natin. So take note, in our build-up section, ito yung build-up section. This is composed of I, yung wide flange, and yung ating channel section. So take note that yung wide flange section natin on its upright position, ito, given dito, yung properties. While for the build-up section, yung wide flange natin is naka-upright pa rin yung position niya. Okay? So the same, upright position for the wide flange. However, dito sa ating channel, yung given properties natin is on this upright position. However, dito sa build-up section natin, yung channel natin is naka-rotate siya 90 degrees. Okay? So, naka-rotate yung channel natin dito. So, if our wide flange section dito sa individual, okay? So, tignan natin dito sa wide flange, dito sa ating individual, andito yung centroid natin for the individual wide flange. Okay? So, as you can see, dito sa build-up section natin, ito yung build-up section natin, yung given na wide flange, yung given na properties, and yung position ng wide flange natin is the same dito sa ating build-up section. So, pagka andito yung centroid dito sa ating individual or yung ating local wide flange dito sa build-up, andito pa rin yung ating centroid. Let's say, andyan yung centroid nung ating wide flange dito sa ating build-up section. Okay? So, whereas for the local channel section, yung centroid niya, andito siya. Andito yung ating centroid for the local channel section, which is actually measured from the back ng channel natin, X. So, yung value natin sa X is 20.27 mm. So, andito yung ating centroid for the local channel section. So, pagkapuntan ninyo dito sa ating build-up section, ang channel natin is rotated 90 degrees. Okay? And then, yung centroid natin is measured X from the back of our channel. So, yung centroid natin dito, pagka punta natin dito sa build-up section, andito yung ating centroid for the channel section. So, andito yung centroid niya. That is 20.27 mm. Okay? And for the wide flange, yung centroid niya, mula dito sa taas niya dito, dyan, yung measurement ng centroid is the depth divided by 2. So, 544.3 over 2 hanggang dito sa top. So, pagka kinuha ninyo from our, let's say our reference axis is from the top of our build-up, ang magiging distance na dito is 544.3 over 2 plus the thickness of the web nung ating channel, which is equal to 18.2. So, yan yung magiging distance ng centroid nung wide flange dito sa build-up section. Okay? So, now, for the wide flange section, the distance of the centroid is measured from the top of the build-up section. We're going to solve for the centroid of the whole or yung build-up for the whole build-up section. Let's say our centroid is here. So, ito, andito yung centroid natin. This is the centroid for the whole build-up section. So, that is a combination of the wide flange tapos yung channel natin. Andito yung centroid niya. So, isosolve natin yung centroid dito. Okay? So, mamaya isosolve natin yan. And then, ano pang? Okay. So, first, to solve for the properties of the steel section, we need to start with the total area. So, area of the build-up section. This is a combination of the channel and yung sa wide flange. And given yung properties ng channel, given din yung properties ng wide flange. So, the total area is simply the area of the wide flange. So, given, ito yung area niya, plus the area of the channel section. So, area, ito yung area niya. Okay? So, that would be our total area. So, we have 9484 plus, this is the area of the channel, and then the area of the wide flange is 15,677. So, resulting value is 25,161 mm squared. That will be the total area of the whole build-up section. Okay? So, next is to solve for the centroid. The location of the centroid. Yung X bar and yung Y bar natin. Okay? So, as you can see in our build-up section, ito, the centroid of the channel and the wide flange coincides along dito sa ating vertical axis. So, pag tinitignan natin ito ang diagram natin, andito yung centroid ng channel andito yung centroid ng wide flange. This coincides dito sa ating vertical axis. So in short, our build-up section is symmetrical about y-axis. Okay? So with that, we could assume na yung global y-axis, yung centroid natin, will be aligned with this y-axis. So ano yung magiging value ng x bar natin? So yung x bar natin is equal to 0 because our centroid is symmetry about y-axis. So, yung isosolve na lang natin dito is yung ating value for the y bar. Okay, so to solve for the value of y bar, gagamitin natin yung Varignon's theorem wherein yung total area, the total area times the centroid, yung y bar natin of the whole build-up section is equal to the summation of the area of each individual section. Okay? So, summation of the area of each individual section. So, this is equal to the area y of our wide flange plus the area times y of our centroid, a channel. Okay? So, for the total area, meron na tayong total area. Ang hinahanap natin dito is y bar. So, our total area is 25,161 y bar is equal to the summation of area times the centroid of each individual section. So, unahin natin yung wide flange. Area niya is 15677. So, ano yung y natin? Yan yung location ng centroid nung ating wide flange dito sa ating build-up section. So, ano yung location natin dyan? We have 544.3 over 2 plus 18.2. So, yan yung sa wide flange. So, ito yan. Itong distance. Okay? Plus, ano yung area ng section? Ang area ng section natin, C-section natin is 9484 times ano yung kanyang distance, yung centroid, yung distance ng centroid from our reference point, that is 20.27. So, times 20.27. Okay? Substituting the values, our y bar now is equal to 188.54806 mm. Okay? So this would be now our location of centroid y bar. Yung x bar natin 0 since our centroid is in symmetry with our y axis. Okay, next. For the moment of inertia, for the moment of inertia Ix, so letter C, moment of inertia, Ix global and yung Iy global. So pagka sinabing local properties, saka yung global properties. Pag local properties, I'm referring to the individual properties of the section, such as yung properties ng given na channel and yung properties ng given ng wide flange. So, yun yung local properties. Pagka sinabi kong global properties, yun yung properties ng buong build-up, yung buong build-up section na, yung pinagdugtong na yung wide flange and C section. Okay, so what we're going to solve here dito sa moment of inertia natin dito is the moment of inertia of the build-up section, yung global properties. Yung entire build-up section. Since yung individual section natin, meron, given yon yung individual properties ng channel and yung wide flange. Okay? So for the moment of inertia, let's start with the global moment of inertia, Ix, with respect to X. So dito, gagamit tayo ng transfer formula. Yung transfer formula natin, which is the summation of Ix plus AD squared. Since yung centroid ng build-up section, so pagka tinignan natin ulit ito, yung ating diagram, yung ating figure. Ito yung centroid ng buong section. Ito lang yung centroid ng C-section, andito. Tapos andito yung centroid ng wide flange. So, gagamit tayo ng transfer formula dito. Okay? So, ita-transfer natin yan from our individual centroid papunta doon sa ating global centroid. Pati ito, ita-transfer natin yan dito sa ating global centroidal. So that will be the summation of Ix. Etong Ix natin dito is the moment of inertia of our individual section. Ang hinahanap natin is the moment of inertia of our build-up section. Plus area times the distance squared. So ito yung equation natin for the transfer formula. So that is equal to the Ix plus AD square ng ating wide flange plus yung Ix plus AD squared nung ating C channel. Okay? So for our wide flange, given yung Ix natin, yan natin yung Ix natin, which is 761, ito yung Ix natin for the wide flange. So plus yung area natin, ito yung area natin, 15,677, times yung distance. Ano yung magiging distance natin? Yung D squared. So yung magiging distance natin, ito, yung centroid natin from our reference is 544.3 over 2 plus 18.2. Ito yung distance nung centroid nung wide flange dito sa buong build-up. Tapos, ang centroid nung global natin, yung build-up section natin, andito. So, ang kukunin nating distance is this distance. So, ito yung distance ng wide flange. Ano yung distance ng wide flange? So, 544.3 over 2 plus 18.2 minus yung ating y bar. Makukuha natin itong distance. Okay? So, that would be our distance. Paano yung sa may C channel? So, ito yung centroid niya. So, ang kukunin nating distance is itong distance. Ito yung distance ng channel. So, from the centroid ng individual doon sa centroid nung ating build-up. Yan yung kukunin nating distance. So, yun yung D doon sa ating equation. So, paano makukuha itong DC? Ang DC, ito, y bar ito, papunta dito, minus nyo yung 20.27 kasi 20.27 hanggang dito. Tapos, y bar ito hanggang dito. Okay? So, yan yung magiging distance natin pagka sa channel. So, yung distance natin pagka wide flange, ito. Okay? So, ano yung magiging Ix natin for the channel? Okay? Given Ix and Iy. Remember, ang given na properties dito is yung naka-upright yung channel. So, pag naka-upright pa rin yung channel natin dito sa build-up section, ang gagamitin natin sa Ix is this value. Iy, ito, pagka naka-upright pa rin. But remember, yung C channel natin sa build-up section is rotated 90 degrees. Okay? So, pagka ito yung x-axis mo, ang magiging x-axis mo dito is andito siya. Okay? So pagka Ix, ang gagamitin mo na dito sa channel, since this property is on upright, tapos naka 90 degree siya, ang gagamitin mo for Ix is the value of Iy. Ito, 4579. Kasi nag-rotate siya. So ito na yung magiging Ix. Ito pa rin yung Ix ng channel natin. Pagkapunta dito, ito na yung magiging Y. Okay? So for the white flange, ang Ix natin is yung 761,704,000. Given yan sa properties, Ix for the white flange. Plus, yung area natin, 15,677. Ano yung distance natin? Yung distance natin is 544.3 over 2 plus 18.2 minus yung y bar natin. At ano yung y bar value natin for y bar? So our value for y bar is equal to 188.54806. So yan yung y bar natin. So etong value na ito yan. Etong dw dito para kunin. Kasi ito yung centroid natin for the whole build-up section. Okay? So, yan yung sa wide flange. Square natin, wag nyo kalimutan yung square. Plus, yung sa may channel. Ano yung Ix ng channel? So, hindi ito yung gagamitin ninyo, yung Ix dito. Since pag naka-upright lang ito yung gagamitin ninyo yung Ix. However, dito naka-rotate nga dito sa build-up section. Kaya ang gagamitin natin yung Ix is yung value ng Iy. So, that is 4,579,000 plus the area nung C-section 9,484 times yung distance. Ano yung distance ng DC? That is y bar minus 20.27 squared. Okay? So, ito yung DC. Ito yung distance natin. So, that is y bar minus 20.7. Substituting the values, makukuha natin yung value ng Ix natin. For our global, or yung build-up section natin, Ix natin is 1,197,316,928 mm raised to the 4. So, ito na yung magiging moment of inertia natin about x-axis for our build-up section. Paano naman yung sa Iy natin? The same. The summation of Ix plus AD squared, Iy AD squared. Okay? So, Iy for the wide flange plus AD squared for the wide flange plus yung Iy plus AD squared for the channel. Okay? So, given yung properties natin, Iy, given yan sa may individual properties ng wide flange, given din dito sa channel. So, dito sa channel, yung Iy natin dito is actually the value of Ix. Kasi naka-upright yung C-section natin sa given properties and naka 90 degrees doon sa may build-up. Okay? So, area, given din yung area. Yung D, ano yung magiging distance natin? Yung distance natin dito is magiging 0. Kasi sabi nga natin kanina, yung centroid natin coincides with y-axis. So, magkakaparehas yan. Yung centroid ng build-up section coincides with the centroid of the local channel. Tapos, coincides with the centroid doon sa y-flange. So, wala tayong distance dito. 0 yung value natin. So, ilagay natin 0. So, ilagay natin yung values. So, Iy is equal to 33,881,000 plus 15,677. Ang distance natin, 0 squared. That is for the wide flange plus for the channel 168.157.000 plus the area 989484 area times distance 0 square. So substituting in our calculator, our IY for our build-up section, moment of inertia is equal to 202.03800 mm to the fourth. So yan yung magiging moment of inertia natin about y-axis in our build-up section. So ito yung magiging value natin. Okay? Next property is the section modulus, our D. Okay, so for our section modulus, Sx for our global and Sy. So ano yung equation ng section modulus natin? Section modulus of with respect to x is equal to Ix over C. Yung C natin is the farthest distance doon sa centroid. Okay? Pag sa x-axis, sa x, and sa y, y. And for the section modulus about y-axis, that is the moment of inertia about y, the build-up section over cy. Okay? So, etong Ix and Iy, na-solve natin yan kanina, meron na tayong values. Ang problema natin dito for the section modulus is the value of Cx. Okay? So, ano yung value ng Cx natin sa with respect to x? Okay? Farthest distance. So, balik tayo dito. Okay? So, etong buong ito, yung buong depth ng wide flange, ang value niya is 544.3. Ito yun. Ito. Yung buong depth niya is 544.3. So, plus yung thickness ng web nung C-section natin, which is thickness of web, 18.2. So, yung buong build-up section natin, yung buong depth ng build-up section natin is 544.3 plus 18.2. Okay? So, yung C natin is farthest distance mula dito sa ating centroid. Okay? Sa outer fiber ng ating build-up. So, pagka tinitignan ninyo ito, mas malapit siya sa top. So, ang kukunin yung C natin for with respect to x-axis is this value. So, ito yung magiging Cx natin. So, paano natin kunin yan? Paano natin kunin yung Cx? So, pagka tinitignan natin yung diagram natin, yung buong depth, 544.3 plus 18.2 minus yung y bar natin, yung distance na y bar, makukuha natin yung value ng Cx. Okay? That is with respect to the x-axis. So, paano naman yung Cy? Yung C. So, pagka Cy with respect to yung ating y-axis, ito yung y-axis natin. Farthest distance, so since parehas yan, ito yung value ng Cy natin. Okay? So, paano kunin yung value ng Cy natin? Just have to divide the depth nung channel natin. Makukuha natin yung Cy. Okay? So, yung depth ng channel natin, 381. Divide nyo lang ng 2 yan. Since parehas ito, andito din yung, nasa y-axis din yung centroid natin. Okay? So, 381 over 2. Yan yung magiging value natin for Cy. Okay? For the value of Ix, yung na-solve natin kanina, ito yung value ng Ix natin for the build-up section, and ito yung value natin for Iy. So, direct substitution lang yung gagawin natin for the section modulus. For the Sx, yung Ix natin is 1197316,928. Ano yung Cx natin? So, kanina, sabi ko, Yung depth, yung total depth natin is 44.3 plus yung thickness ng web, 18.2. So, i-minus natin yung value ng y bar, which is equal to, ang y bar natin is 188.54806. Okay? So, ano yung magiging value natin ng Sx? Section modulus with respect to x-axis is equal to 201,793.599 mm cube. Okay? So, this is mm to the fourth power over mm, magiging mm cube. Okay? So, for Sy, ang Iy natin, yung na-solve natin na Iy is 202,038,000. This is mm to the fourth over yung Cy natin is 381 over 2. So, anong magiging value natin dito? This is in mm. So, magiging mm to the third power. So, 1,060,566.929 mm to the third. So, kindly check. My calculation is correct. So, ito na yung magiging section modulus natin for Sx and for Sy with respect to y-axis. And lastly, for the properties, yung radius of gyration. So, pagka meron ka ng moment of inertia and area total, mabilis mo nang kunin yung radius of gyration, yung Rx and Ry, nung build-up section, nung full section. Since Rx and Ry of the individual properties ng section is given sa manual. So, ito ang kukunin natin is yung sa build-up, yung sa global. Okay? So, section modulus Rx is equal to ang radius of gyration natin is equal to the square root of the moment of inertia over area total. So, yung Rx natin is Ix over area total. And yung Ry natin is the square root of Iy over area total. So, you just have to substitute the values na solve natin yung Ix. Yung Ix ng buong section ito. Total ng buong section. Okay? So, substituting yung values natin, ang Rx natin is 218.14 mm and our Ry is 89.61 mm. So, this would be now our radius of gyration with respect to x and with respect to y. So, yan yung mga properties ng steel.